Yeah, Bluetooth is still an open research problem. So yeah, like I was saying, one of the first things I remember about RL is when AlphaGo released it all, and that was like a big breakthrough for RL. And I was still in my undergrad, and I was just blown away. So another thing that happened with RL is when DeepMind's AlphaStar reached most of the human startup. And this had a big impact on my thoughts and interests because startup was really big in my undergrad days and like used to play all the time. And for anyone unfamiliar, StarCraft is basically a PvP player versus player battleground kind of game where there are two teams. And so in this picture, you can see there's one team with this dark blue kind of it's sci-fi objects where they can shoot and kill each other. And naturally, being a AI enthusiast, I framed my first AI question, which is how to kill my friend off him. So, starting from there, I quickly realized that the solution is not so simple, and I did the first roadblock, which I think most of us has hit with AI, which is efficient. So, AlphaStar literally played startup for 200 years, and you're reading it right, like non-stop for 200 years, and that's simply something I couldn't do, so I couldn't kill my friend optimally. But more importantly, as we scale and as today and fast forward today, we are trying to apply this to different real world problems. Like we have this client with the army, and we have to deal with a lot of high fidelity simulations. And there the so high fidelity simulation to put it simply just requires way more training data than like even the kind of games that IL is good at. So that's like a big block. And speaking of games RL is good at, we all know how good RL is at Atari games. It's pretty much solved it. Except one problem, which is you often don't get an explanation. You often see that the games are played and we get 99% accuracy, but when it fails, you don't know why. Or sometimes they might even find shortcuts that, just say hacky solutions. But really, you want to know why. And yeah. So one of the things I asked myself that what's the problem? Because people are coming up with newer and newer algorithms and AI is solving everything. Is it really the algorithm or is it the simulator itself that's the most fact? And then that led to me thinking more about what are the typical problems for RSM. And one of the main proponents or one of the things is model-based simulators, and often the issue with them are that they are tied to a specific scenario or a specific algorithm. So that's like super inflexible. Even if something good, we cannot use it for everything we want to do. The second thing, which is like there's no problem with having a markup assumptions, except the fact that for most real world cases, it doesn't work. Again, just to explain, markup assumption is when your next state depends only on your current state. And as you know that the fact that I am here or you are here today depends on a lot more than just what you were doing 5 minutes ago or 10 minutes ago. There's a bunch of actions that we have taken for whatever for us. So again, it doesn't hold for any of the assumptions. So here's what like I have tried, and this is what I've come up with so far, and here's what I'm proposing. So this is called PyReason theme, and the reason it's called PyReason is that it's a clever wordplay, but also it's like a Python-based reasoning open source thing that we have come up with in-house, and this is the simulator built on top of that. So, so what we propose is a semantic proxy for simulation for R, and that's based on temporal extensions to annotated logic. And it should have the ability to perform multi-step open world reasoning. So I'll come to many of these and what it does later. So here's the salient features. Again, I'll show you some results going forward. So it's open source, so it's on GitHub. Anyone can go and play with it and build it and make changes for their own application. it's scalable. That's another big issue. Like I said, the efficient scalable kind of the same thing for RL. It's extendable and it's like a symbolic extendability, and I'll show you what I mean by that. Modular, you can learn something for a particular environment and then go and like use parts of it for some other application again. It captures on Markov dynamics. We also have some things that we've incorporated to allow safety constraints. So specifically for those who are who know about RL, it's popular right now in the literature called shielding. But typically shielding is only within the reward function. What we have done is extend it to the environment itself. And then it's also algorithm agnostic. So what I mean by that is it should be working with any algorithm really. So here's what I mean by algorithm agnostic. So plug in any algorithm or policy here on the left, and then the rest of the structure is made in such a way that it works with that. So just walking through the structure. So like I said, PyReason is a Python-based reasoning engine that you come up with. PyReason Gym is, as the word says, like it's like an OpenAI gym-based environment, which really is something that sits between the reasoning software and your favorite RL algorithm. So the algorithm or policy as standard will give an action or policy, an action, and then this will be converting it into facts, and then the reasoning engine generates inference, and we get back reward and observation. And in addition, what we're saying is that this inference engine also provides symbolic explanation. So all the reasoning engine really needs is a knowledge graph representing the world that you're working with and a bunch of rules. These are first order logical rules which I'm showing you in a minute. So here's like toy example of the kind of game we have tried to use for this experiment. So just checking out my time. Just to show you so this is like a grid world, and then there are some obstacles in the middle which are like shaped like mountains. There are two teams, and if I display this through, each of them start from one corner, which is the starting base, and then the objective is to either kill the enemy like the red agent does here, or try to reach the opponent base while the opponent is not there. So here's the building blocks if anyone wants to play with this. So first we define the objective, like I said, about killing or capturing. Then we model the environment dynamics with some logical rules, and then we design the reward function. So this 2 and 3 are basically what you need to do for your own experiment. So how do we do that? It's really simple. So again, for this game, let's look at like a simple movement. Everybody, if you just look at your monitor for a second, bottom right corner, you see that the red agent moves one step up. So this dynamics, how we represent in the model itself is what I'm going to show you here. So first, the agent chooses an action. So the agent itself is represented by the first clause, which is agent A11. Here 11 is just the truth. So if it's 0, it will be false, something like that. And then choosing an action, so we have move direction. And then the up is simply like what action. Again, 11 means it's true that it's moving up. Then we ask simple questions like where am I? So we are at location X. Where do I want to go? We want to go to Y, which is upwards from X. And can I go there? So we check if Y is blocked. So it's really simple, like forming this logical, it's not really that difficult. And yeah, of course, if this happens, then agent may execute this action in one time. So and this is like a generic rule base, and I will show you how you can easily form a reward base as well from a rule base. So the first rule says that agent can use when X from Y. This is basically the example I showed you. And so basically it says, okay, if this is satisfied, it's a valid move, and so we assign a reward to it, saying, okay, if this rule is fired, then it's -2. Similarly, rule 2 says if it's an illegal move, what happens, and then if that rule fires, we assign a reward, which is -200. And again, the third one says, okay, what happens if you die or you kill the enemy, you get some rewards or you lose some rewards. And finally, the last one is if you are the last survivor, then you get +50 points for the win or -2. This very RL that as we know right now is just how we form it directly comes from. And finally, the other important thing is an explainable case. Like I'll show you, and you'll see soon that it's very useful for debugging or reward shaping. So, like I already showed you, this same rule. If this rule fired for again the same case, with moving from bottom right to the one directly above it, the square directly above it, we see okay, what time step did it move in the first time step, which agent, the red agent, and then it gives the indices of the squares from which it started moving and where it ended up. And finally, which rule fired, you only have one confirmed example. If you have like a trace like this, it's very easy to go back and see, okay, which rule is fired in what order, and you can debug your that. So this is like a big version of the same thing, how it comes out, and you can have like places pretty large. You can have a machine learning model go and analyze it. This plot shows that PyReason as compared to StarCraft we talked about, or the military sim which is abstract scales better in time significantly. Like we get up to 3 orders of magnitude. And with this, like this chart with a lot of numbers basically shows that if we train a policy in PyReason, which is faster to train in PyReason and then go and use it in any of the popular sims, we get pretty similar numbers for rewards and win percentage. We can do that and pretty much expedite our training process. So there's a bunch of future work I don't have time to do it, but we can talk about it. Here's one which is about robotics, how we are trying to bridge the sim to really have it. And yeah, this is all about it. And here's like we have a YouTube channel where we have some small videos in that. And we have a website with all the resources. Explain. Thank you.
Okay. Questions for Kristen? So, thank you for the presentation. So, does this also work with multi-agent bots where like 2 or 3 bots have to collaborate with each other to attain a single objective?
Yes. We have also done one experiment that two bots. Yeah. It works. And in our paper, we explain the changes that we made.
Other questions?
Thank you. I know this sounds like an odd question. We haven't heard of StarCraft before, but I am curious. Does anyone ever look at what you might want to do is look at what 0.2% did that one, right? That's interesting.
I did not look for StarCraft, but when the Go came out, I remember what happened. So Lee Sedol won one game, and basically the experts analyzed it with a bunch of engines, and they said that what he played was like a miracle move. So it's like, and if in terms of machine learning models, it will be like an out of distribution move. And that's completely expected because like that's kind of where the failure rules come from for these black box models. So it's a bit out of the way, right? In terms of chess, I would say it's like a brilliancy or something like what you don't expect in a standard strategy you've never seen before, so never trained before, something like that. But most of these out of distribution ones would be a bad move. There's only a few situations where you can do something that takes at least for these games where you have big rules and something the search space is to be technology. And it's a nice.
And did we have one more?
Thanks for the talk. I think my question is more related to user producing sense that as you mentioned, it would require for the domain expert to provide all the rules of the knowledge graph behind, which seems to be at least thinking from the user side, strong engineering requirement. So, there are any ways, what of thoughts on that direction as to how those things happen? The point being that this can be extended to even much more complicated domains such as fundamentals.
Yeah, definitely. I completely agree with you. And these, like the second two are something that we are looking at in the lab itself. And especially like learning logic program from data is it's a small segment of literature or differential like that's in a nascent state, but it's still. And honestly, I think like at least for the current example, like, we can do it pretty effectively. But yeah, I mean that would be the next step, and which would be directly fitting well into what is. But I agree. I mean, for a lot of cases like this.
Okay, let's thank the speaker. And so next we have Noel and Nathan. That seems to be is Semantic. Okay,